Everybody?
Welcome. First time?
Back from Oxford.
Ah, right. And,
An important announcement is being made.
yes, the announcement
Welcome
being,
back.
I'm very pleased to announce Don Zagier from Bonn and Paris.
Currently from the Newton Institute in Cambridge.
So, triple affiliation. And he'll talk about finite versions of multiple zeta calculus.
There are no versions in the title, just finite. Okay, so we're being possibly joined on this by my well, part of this work I started alone, and part it's not really work, it's the part I did, it was computer things. The part is joined with Masanobu Kaneko, who is possibly with us right now because he said he might be watching this from, you won't see him, but he might see you. He's going to try to watch this by streaming web or whatever these things are called in Japan, but he has no idea if it'll work. So if you're there, Masanobu, hello, and but he can't wave back. Okay, so first I'll just tell where the story starts. So 3 years ago, I think I was in Taiwan for a couple of weeks and gave a series of lectures. And there was another invitee there who was from mainland China called Jiwei Sun. And he gave two rather remarkable lectures, one of which I think had 50 and one of his 80. Conjectures, maybe my memory exaggerates, but there were dozens and dozens of conjectures, one after the other, all that you can find on his website, and all of things he had checked numerically very far. Very beautiful, all of them surprising. And so one of them, I solved it in those days, and we wrote a little paper together, but another one looked very intriguing, and so I started playing with it, and then things generalized more and more, and so the original thing that he had conjectured, that particular special case, I heard from Masanobu, he's now proved and published, but at that time they were all just experimental statements. So now that part is no longer experimental, but there's a lot more, and essentially everything I will say today is experimental. Well, there are a few things proved, but nothing very deep. So the most fun thing is that I'm going to be working in a certain ring, which I'll just write script A, but I might forget and call it script R because I was using R and now we changed to A. So A is supposed to remind you of the Adels. So think of this as kind of the poor man's Adels for people who can't afford the full version of the Adels, which is this very difficult thing, QP colon ZP or something. There's not even a notation for it, where you take the product over all primes P of the p-adic numbers, well, at least the finite Adels, and then you require that almost all of the components are integral. So it's kind of an intricate thing. This thing is much, much easier. You take the product, ordinary direct product over all primes of, since I'm an American, even though I'm in England today, the integers will be called Z and not Z, unless I remember. And so you take the product. So in other words, you simply have a residue class modulo P for every prime P, but you consider two such infinite collections as the same if they differ in only finitely many positions. So it's the quotient of the infinite product by the infinite sum. So if you're one of those people who, for intellectual laziness, say, I don't distinguish between infinite products and infinite sums, who cares? It's just, you do something, and then there wouldn't be much left here. But so it's kind of important here that the product and the sum are not, in fact, the same. So this is the object, and we're going to find lots of interesting numbers in this, some of which are multiple zeta values, and that's which should be zeta, if I call ZZ, should be consistent. We'll find there are many other interesting numbers, but I'll only concentrate on these finite zeta values and also on the, I call harmonic moment sums. So we're going to have finite multiple zeta values, and we're also going to have harmonic moment sums, or some sums, it's a little hard to say, which are the generalization about the thing that his original conjecture had to do with. So these will be two special classes. But first I'll show you that this is kind of a fun ring to work with. And I was very, very happy, or to translate into British, chuffed, when I talked to Maxim Kontsevich a few months ago, and he showed me very excited some wonderful things he'd been doing. I mean, orders of magnitude deeper than anything I'll tell. And the key player, or one of the key players in his story, was exactly the same ring, which he was looking at for entirely different reasons. And therefore, although he hadn't thought of putting multiple zeta values in there, he had other things, some of which I'll mention. And when he saw the multiple zetas, he quickly had a suggestion, which turned out to be worth its weight in gold. So you'll see it later. It's a suggestion that turned out to cast a lot of light. So the only interesting idea in this whole thing is due to Maxim Kontsevich. And that's a slight exaggeration. Okay, so first let's just start with this ring, and there's just a few simple elements. So I'll give a series of examples of elements of this funny ring. So the first one is rational numbers. So it's clear that if you have a rational number, like for instance 14, for all, of course, with some integer. And that integer, well, it's only unique modulo p. I could take it if I wanted between 0 and p minus 1. There's no reason to do that. And so I can take these numbers. A2, A3 isn't defined, but I take anything I want. Because remember, the definition of the element in A is you can throw away finitely many terms. You can just omit them or choose them at random. It doesn't really matter. So it's clear that rational numbers map into this A, and it's also very clear that it's injective. Clearly, a rational number which is 0 modulo infinitely many primes, its numerator is divised by infinitely many primes and therefore vanishes. So this is an injective map. So A is a Q algebra. And in fact, if you think about it a moment, you see that if I call A0 is just the direct product of Z modulo PZ, then this is a ring. Of course, it's a direct product of rings. It's a ring over Z. And the thing that I divide it by is simply the torsion. So A is this, and in this case, it's the same as A times Q, and it's also the same as A tensored with Q over Z, or Z. Okay, so, but I won't ever look at A0 again, because it's really, although these finite metal Z values, as it happens, are already in A0, so there is a notion of integrality, but we're not going to use it in that form. Okay, so that's the first example. Now, the next example would be Fermat quotients. We'll quickly look at the paper to see if we chose. Oh no, the next example I didn't want to do Fermat quotient yet. I want to go to the harmonic moment sums right away, because that's the, as I said, the motivating example for this whole story. So define h of n to be the nth harmonic number. So if I make a little table, then it starts in 0, 1, 3 halves, I think 11 sixths. So these are extremely complicated rational numbers. The denominator is huge. So it grows exponentially with n, but anyway, here they are. And now, as I said, we're going to take harmonic moments. So I'm going to take the sum, h of n to the power j, and sum over all n. But actually, I want even slightly more general sort of weighted moments. So these are going to be the sums I actually look at. Let's call this v of ij. And so for each prime p, I can take this sum where now I only sum for n between 0 and p. And I consider this thing modulo p. So that certainly is a well-defined number modulo p. And here, in fact, it's defined for every p, because since n is less than p and these numbers are less than or equal to n, everything I'm inverting is strictly between 0 and p, and therefore invertible mod p. So this gives me a number v of ij, which actually even belongs to a0, to this smaller thing, but I'll just project it down to a. So it's a, so this is just the collection v of ij. I mean, that'll be my notation in general. An element of a, so a typical element of a, will be denoted as a collection of numbers where I write the prime in parentheses, meaning the pth component.
So what's the difference between the two a's?
Oh, that I forgot. This is equal to a. In the paper we use this, and I thought it would be easier to write the one I usually write, but of course now I forgot. Thank you.
We always identify also over there.
Absolutely, yes, you should have asked this question much earlier. Remember,
Too fast.
what an excellent question. So a equals a, but it's different from a.
Yeah, yeah.
What is a mod q?
A mod q doesn't make any sense at all.
Q is embedded in A.
Well, I mean, it's just a vector space, but it's not a ring. I mean, it would be like taking, for instance, q of the cube root of 3 is a nice number field, but if you divide it by q, you just have a two-dimensional vector space. It doesn't really make much sense. I mean, the thing you're dividing by isn't
So
ideal.
like in the infinite space, you do get something.
Yes, but that's not what we're doing here.
Yeah, I
And it's not at all the same. I mean, it's actually a very weak analogy. No, in the case of A, you can divide by Q, although actually it's not even true. If you take the finite integrals and you divide by Q, you get a total mess. You only get something nice if you multiply by R. Anyway, we don't want to divide by Q. That would be exactly like in the number field. Okay, so here's my second example. So this is my example 2. Therefore, are these, I don't want to write it all again, so it's the harmonic moment sums equal to some sums, or some sums, it sounds nicer. And then here they are, so it's these numbers. So what he had discovered very explicitly is that, what he actually wrote is that for every n, for every prime p experimentally, and then as I say later he proved it, I mean he had many conjectures like this, but there was no particular pattern. They weren't tables, they were just individual statements. Not all that all of this form, he had many types of conjectures, but he had 2 or 3 of this general sort with various powers. So what he discovered is that this thing is congruent modulo p for all p bigger than 3. Which was experimental then. I proved it easily, and he's also proved it, and it's written up. So this was a typical case, but in our new notation, I can just say that v of 2, 2, see this is the pth component, but it's for every p, but this is the pth component of the rational number minus 4 9ths. So I can just say, since q is now contained in A, I can just, which is equal to round A, I can just say that the number v of 2, 2 is a rational number. It simply happens to be in this subspace. But it turns out when you go further, there are lots more, and I'll come to that later. For instance, I'll give 3 examples, just the ones that we type now to the introduction of the paper. So here are 3 more v of ij's, which turned out to be rational. V of 6, 2 is 76 over 2205. The denominator is very small primes. The numerator is whatever it is. Here the same. The numerator has some random prime factorization, but I mean, it's part of a big table, so I don't know this particular number, but in general, there's no prime factorization of the numbers, but the denominators all only involve small primes, and it's all very systematic. So now when you see this, you could say, so the theorem is Vij is always rational. That's not true at all. But what is true, so here's the theorem, this I can actually call a theorem because it's a little theorem. So V of I, now here I didn't say where I and j run. I was criticizing the habits of physicists this morning that they don't remember always to say where their variables lie, and then I didn't do it. So j is an integer. I won't write integer, believe me, it's an integer greater than or equal to 0. You really don't want to take 1 over h. But I, since you see that n is between 0 and p, you're perfectly entitled to take I positive or negative. And actually they're both interesting, but for the moment, as you can see in these examples, I and j are positive. So the theorem is that for all I greater than or equal to 0, v of I2 is indeed rational. I mean, so is v of I1, or is it v of I0? If you go back far enough, then they become totally uninterested. They're all 0. So that's certainly rational, but not, of course, terribly interesting. So sorry, I absolutely want to start with 1. V of I2 is also always rational. V of I3 is also rational. But V of I4 is also rational, as you see in the example, if, and conjecturally only if, I is odd. And after that, they're conjecturally never rational. So that's a little strange. So if you write this as a table, the first 3 columns consist of rational numbers. The third column is half rational and half isn't. And the fourth column, and the fifth and higher columns have no rational numbers at all. Is that me? Feedback? No. So this looks like a non-theorem, and that's, well, and there are 3 statements, but then it looks like it just falls apart. But actually the correct theorem is that for fixed j, V of ij lies in a finite dimensional subspace in A, which this finite dimensional subspace depends on j. So for j equals 1, it's q. For j equals 2, it's q. For j equals 3, it's again q. But for j equals 4, it's presumably 2-dimensional. What I prove is that it's generated by q plus a certain number, which I'll call z3, which I'll define in 2 seconds. And then z3 is conjecturally not in q, and at least to many hundreds of digits, it's not in q. So this is in A and presumably not in q, but that's conjectural, just like this is meant to be zeta of 3. And of course, in the special case of zeta of 3, up here we proved for us that the real zeta of 3 is not a rational number, but for this new one, we don't know it. So there's some kind of an analog zeta 3 that I'll come to soon, and you get this. And similarly, if j is 5, then you get, now I have to look at the table so that I don't mess up the numbers. If j is 5, it's again q plus q zeta of 3. So in other words, it's a two-dimensional space, and if j equals 6, then it's this plus another q times one more number, and so on. So so there is a theorem for every j that it's in a finite dimensional space. You get lots and lots of relations. And the reason for this odd thing is that, well, these numbers I didn't tell you, but v of I1 turns out to be on the nose with the usual normalizations, the ith Bernoulli number, and v of I4 turns out to be some rational number plus the same Bernoulli number times z3, possibly times a number like 10 or something. I'll have to look up in the table. It's 2 in this case. So since the Bernoulli numbers are 0 for half the time, then that is the reason that half the time you get.
Is that result for VI1 something with a name in the...
Yeah, trivial. It's called trivial.
It's called
It's
trivial.
completely trivial, yeah. Okay, VI1 is not interesting at all. It's not quite obvious that it's trivial, but it's with a little footnote, it's trivial. It is trivial, non-obviously. Okay. After a week of thinking, you'll see.
Exactly.
No, it would take 10 minutes. It's undoubtedly in the literature in many equivalent forms, but
it will
it's
take much too long for you to do it during my talk, because otherwise
Okay.
there's danger.
okay. So let me continue with more examples. So the next example, now I've forgotten the numbering, but that was 1 and 2. So 3 I've already written, but then I decided to do the sound sums first with Fermat quotients. So I'm just doing it exactly the order of the introduction to our paper, so I don't get confused. And I'm checking my notation. So if x is for the moment an integer, then Fermat's little theorem, as it's called, it's not that little, it's only little compared to the big theorem, and has the advantage that it's a theorem. Okay, it says, as everybody knows, that if p does not divide x, then x to p minus 1 is congruent to 1 mod p. So if I made a new number in my a, like this, if I took that, then that wouldn't be very interesting, it would just be the rational number 1. So that's not what I'm going to do. But number theorists have looked for a long time at the question whether this is true modulo p squared. And so to know that, of course, is the same as subtracting 1 divided by p and looking at this mod p. And so these numbers have been very much studied. For instance, they're very much connected with Fermat's last theorem, and already in the 19th century it was known that if some good thing happened for this, like it wasn't 0 mod p, then you could do certain cases of Fermat's last theorem. So this has been much studied, and for instance, it's very well known, except I've forgotten, I'm almost certain it's 1093, and one more known prime, which is, I think, a few billion, one more known, at least when I last checked, you have that 2, the p minus 1 is congruent to 1 mod p squared. So the conjecture is if you fix x like 2, then there will be infinitely many p's where this congruence is true, even not that are p squared, but they're extremely rare. Like here, up to 1,000 there are none, up to a few billion there are exactly 2. One fairly small and one rather large, and you expect it to be like log x. But I don't care about that. Whatever it is, x to p minus 1 over p is something. And so I call this f of x, the pth component of f of x. This is the definition. And so that gives me an f of x in a. And in fact, you can easily see that this makes sense also if x is a rational number. It makes no difference. For all but finally many p, people divide neither the numerator nor the denominator of x. This congruence is still true, so we actually have a map from q into a, because the finite number of p's occurring in the numerator and denominator of x we just throw away. In the definition of a, we ignored them. Okay, so this is the Fermat quotient, and now it's sort of obvious that this is, you should think of this as, so I should have maybe called it L, I called it F for Fermat. It's the a version of the logarithm. Or maybe the negative of the logarithm. There's a little bit of confusion about that, because it's utterly trivial to check that f of x times y is equal to f of x plus f of y. So in other words, this map, it doesn't go from q because 0, it's not defined. It goes from q cross into a, and this is actually homomorphism. That's what I just wrote, where this is a multiplicative group structure, and that's the additive one. Okay, so that's a very simple example about which I'll say no more, but just to show you that some familiar numbers are in there. Then the next one I'll call the Wilson quotient. Here there were many, one for every x. Here there's just one. So another classical theorem of number theory tells you that for any prime of p minus 1 factorial, this is Wilson's theorem, is congruent to minus 1 mod p. A very famous theorem. And therefore I can make the Wilson number, which is now a single number, WP, is simply the corresponding quotient mod p. Well, I can put equal, I can put congruent, whichever you prefer. So this is the definition. So this gives me a particular number, W and A, about which you can say nothing. It's presumably transcendental or something. But according to Maxime, you should think of W as the exact analog of Euler's constant. I think without a mind, it might be up to sign, but we checked it and it seems to be that way around. So, and he had some argument. It's not directly connected to the log, but there is some argument that I'll skip to do with the gamma function. But anyway, it's just a number, just to show that there are other amusing numbers, but it might come up in some other context. And then, so it's a little like with multi-zeta values, the fun isn't individual numbers, but relations among the numbers. Like before, when I told you, I haven't yet told you what Z3 is, but if all of the VI4s are combinations of 1 and some Z3, then any three of them are linearly dependent. So that makes sense. And in the same sense, if this W comes up somewhere else, it would be interesting, but so far it didn't. Now the next example would be zeta values, ordinary zeta values. So you might think, and that's what I will do, in fact, very shortly for the multiple zeta values, but you might think, let's say I'm interested in zeta of 3, you might just try this, 1 over n cubed. After all, zeta of 3 is the sum 1 over n cubed, and here you can't go beyond p because 1 over p cubed doesn't make sense. Of course, you could omit it and take the infinite sum, but that wouldn't make sense. But this is no good because it's easy to see that this is always 0 if p is bigger than, well, 4. And in this case, it's always 0. But okay, and the reason is simply the map that sends n to n cubed is a homomorphism from fp star into itself. So its image is a subgroup. And unless this index is divisible by p minus 1, which it isn't for large p, then that subgroup is non-trivial, and when you sum roots of unity in a non-trivial subgroup, of course, they add up to 0. So that wouldn't be interesting, but in fact, you can do something else. And so my value of, I'll call it capital Z of 3, so it's exactly the number that, actually I called it capital Z sub 3, the same number that occurred before. I'm going to define in the following way. Z3p is going to be with the plus sign, it's going to be the p minus third Bernoulli number divided by p, of course, mod p. So that's a perfectly good definition. I should perhaps remind you briefly a little bit about Bernoulli numbers. So I remember that the usual zeta function, according to Euler, zeta of 2 is pi squared over 6, etc. And zeta of 2 of r is pi to the r times the rth Bernoulli number times something very simple, if r is even. But Euler also found a way to define zeta for negative r's, and there his result was that the values of the Riemann zeta function, which of course didn't yet exist, and its analytic continuation, which also didn't yet exist, but the values he defined it of the sum of the negative powers of positive integers is minus br over r. So for instance, for r equals 2, I remind you that Bernoulli numbers themselves, I won't repeat the definition, everybody's seen it, but just to have a few in front of yourself. Here are the first few values. Okay. If you need more, oops, I know, plenty more. Okay, so they were possibly not first found by Bernoulli, but by Seiki in Japan. But anyway, at around the same time, it's not known who was first.
Zeta 0 minus 1.
Sorry?
Zeta 0 is minus 1.
Oh, sorry, this is only true if r is greater. In general, there's a minus 1 to the r, but r is always even, as one sees here, for r equals 2. So yeah, indeed, r equals 1 is an exception. Thank you. Zeta 1 is minus 1. Okay, so now the famous theorem, or a famous theorem about these numbers, is that this br over r, or zeta 1 minus r, there are two famous results. So this is von Staub-Clausen, and maybe Kummer-Converts, I forget who's what. It's first of all that this is, well, of course it's a rational number, but it's a p-adic integer if r is not 0, modulo p minus 1. So even if there's an r in the denominator, it'll go away. So for instance, if I continued a little to 10, then I have 5 over 66. So b 10 over 10 is 1 over 132. So that had nothing to do with anything. I didn't want that 5. That's somehow an example of something. Forget it. But anyway, not only BR, but even BR over R is a p-adic integer if R is not a multiple of p minus 1. And what's more, it only depends, in this case, so then, this thing depends only on R modulo p minus 1. In other words, its value is modulo p, repeat periodically with period p minus 1. So if you have a sequence of numbers, you start at 0 or at 1, and they have something, let's say this period 5, so you have A, B, C, D, E, A, B, C, etc., to infinity, then of course you can also extrapolate backwards. There's a completely canonical way to do it, preserving the periodicity. So we can now go backwards, and so if you think about that, you see that this thing, morally, BR over R, so this is, sorry, I didn't mean over P, excuse me, it's over 3. Herbert, why didn't you stop me? I wrote an impossible number. This thing had a denominator. You can't reduce a number that has a p in the denominator, modulo p. But you can if it has a 3 in the denominator. So please pay more attention, audience. I'm going to make mistakes. I'm just testing you. But you really have to do much better than this. Okay, so bp minus 3 over 3 is, of course, the same as minus bp minus 3 over p minus 3, because we're working modulo p. And so what I told you, this is equal, so to speak, to zeta of 1 minus r, where r is p minus 3, but it's only congruent to p minus 3 modulo p minus 1. And so it might be minus 2, right? Minus 2 is congruent to p minus 3 modulo p minus 1. And then zeta of 1 minus r would be zeta of 3. In other words, the natural way to define zeta of 3 is to say zeta of 3 belongs on the negative side. If I change the sign, 1 minus r, it corresponds to zeta of 1 minus r with r negative. But for r positive, we know these things as rational numbers, so we can reduce them modulo p, and then they're periodic, so they naturally extrapolate backwards. So let's extrapolate backwards. And so this is really the natural definition. You might ask why I didn't call it zeta of 3 sub p. You'll see in a moment I'm going to use zeta for something else, and in fact that one is 0. So we have this definition. Of course, you can now do it for any other k. You just put k. You just replace every 3 you see by k. And so now you see that this is p minus k, but by periodicity, this is the same as 1 minus k, and so it should really correspond to zeta of k. So this is the natural analog of zeta of k, and it's this number for which the theorem that I told you before is true, that v of I4 and v of I5 are linear combinations of 1 and z5. Maybe before I go on, so I'll change my, well, no, I'll do my planned order and then hit the other thing. So example 6 is now the one you've all been waiting for, multiple zeta values, which is the subject of the talk. So now if I've a tuple of weights, which are natural numbers, well, I remind you that the usual multiple zeta values, well, there are 2 definitions, both of which I use a lot, but they're in opposite orders, but today it's increasing. So you sum over increasing sequences of integers, R tuples of strictly positive integers, which are strictly increasing, m1 to the k minus 1 up to mr to the kr. And this is a real number, where here, as I said, the ki's are natural numbers, but ki, the last one, should be at least 2 for convergence. And so to get a real number, I need what's called an immiscible index, and an admissible index is an R tuple, a tuple of positive integers whose last entry is at least 2, or its first entry if you prefer the other ordering. Okay, but now I now make the analog zeta A. So zeta A, where this is the round A, but I'm consistently using the other one. Zeta A is defined, well, to define it, I have to define it by its pth component, modulo p, and of course it's now just what you would expect. You sum over R tuples, which are between 0 and p. So as I already told you right at the beginning, this is not the same as this Z3 I defined a moment ago when it's just zeta. So zeta A of 3 is simply 0, which is not the same as what I called Z3. So there are 2 sort of canonical and natural ways to generalize ordinary Riemann zeta values. The first one, which is slightly less obvious, with Bernoulli numbers, that works in that you get non-trivial numbers for only, of course, for only for odd k. So here, k must be 3, 5, 7. Otherwise, it's not interesting because z2, z4, and so on certainly exist, but they're all 0 because, as we saw, the Bernoulli numbers with even indices, with odd indices vanish. So here you get only the odd zetas, but you only get them with this definition. If you take the obvious definition, then this thing would be 0. But it's not 0 if you allow the multiple zetas, so we get interesting finite zeta values. So that's my last thing, and these will be called finite. So the name of such a thing here, we'll call this the finite. It's not a finite number, it's the finite analog. But later we're also going to have finite numbers, which are multiple zeta values. Okay, so that's the last one. Now before I proceed, let me make kind of a non-example. So something which isn't in A. So here's an example of a number that isn't in A. So rational numbers, we saw right at the beginning, are in A. And the reason is, if you take a rational number like 14/9, that means 9x minus 14 equals 0, it's a very easy theorem that this equation has a unique solution modulo p for almost every p, all but finitely many. And so you can take those. But let's say that I wanted an algebraic number. So my non-example, I guess it's the first non-example and the only one, is algebraic numbers. So irrational algebraic numbers. So I'm going to make two claims, both of which are true, and that A contains no, well, except the rationals, of course. So it contains no algebraic numbers, except obviously the rationals. And the other claim, which at first sight you might think contradicts the first claim, is it contains infinitely many irrational algebraic numbers. So they're both true, even though infinitely many is not none. But it's a question of how you define things. So let me explain that. It puzzled me for a while, because I somehow managed to prove both statements and then I felt uncomfortable. But then I learned to live with it. So let me show you. So let's take, what's an algebraic number? So here's a simple algebraic number. X is the cube root of 5. Okay, that's an algebraic number. And every algebraic number looks like that, in that every algebraic number, you can't always write it with surds or with powers, but you can also always write an algebraic number as the solution of some polynomial equation with coefficients in z. And of course, you can reduce that thing mod p. And now, if this thing had a unique solution modulo p for every p, that would be my algebraic number. And even if it had at least one solution, I could pick one. You don't need the axiom of choice. You could take, say, the smallest one, smallest positive residue, which satisfies this. But the problem is that there exist infinitely many primes such that x the cubed congruent to 5 mod p has no solution. And so, in fact, the little lemma is the same is true, not just for x cubed minus 5, but for h of x, let's call it f of x congruent to 0 mod p, has no solution, mod p. And here, h, f of x, is an irreducible polynomial over z of degree strictly bigger than 1. So every algebraic number which is irrational, by definition, it's in the algebraic closure of Q, it's the root of some such polynomial, and I claim that that number cannot be listed. So this algebraic number does not exist in any reasonable form in A. In other words, there's nothing in the ring A whose cube is 5. Well, it's easy for 5, but actually it's easy in general. I'll sketch the proof. It's kind of a little fun. So we take this, let's take an actual number. So alpha is in Q bar, and it's a root of this thing, so it defines a number field, let's call it K, which is Q of alpha, which is some degree N over Q. Well, the degree, of course, is just the N is equal to the degree of F. And of course, somewhere above that, you have the normal closure, which is a Galois extent. So this thing is a Galois group, which may be huge, it can have order N factorial, and this thing corresponds to a certain subgroup, which is not normal in general, but has index exactly N in G. So now it's very easy to see that in this setup, f of x has many solutions. Now I have to get it right. So for instance, f of x will have n solutions in P. It'll split completely exactly when the Frobenius element of a P, which is some element of the Galois group, lies, it's trivial in G mod H. So that's the extreme case. So the number, I'll just say the number of zeros, you have to think it out. I can't do it in real time. I didn't prepare this thing and I've forgotten my own argument. The number of zeros of f mod p corresponds, of course, that's very well known, to the position of an element called the Frobenius element which is in the Galois group of q bar mod q, but therefore you can reduce it. It's therefore in, this is a quotient, a subgroup of that, so it's in n. So you have an element here, and you're interested in the position of n in the quotient, in G, in the position of this thing in G modulo H, so this thing of degree n. So what you have to show is that you get something non-trivial, and so if you think what it comes down to showing is that if you take the union of all of the conjugates of H, then it's, of course, it's contained or equal, but the claim is it's contained but not equal to G. So I claim this is always true for any group, G, and any subgroup H, proper subgroup. And that means that there's at least one element of G which is not conjugate to anything in H, and then by the Cherepanov theorem, that element of the Galois group is the Frobenius element of infinitely many primes, and so there'll be infinitely many primes with no zeros. And to prove this is a standard lemma. I remind you of the proof when I put the inverse here, it's easier to write. This thing only depends, no, it's easier the way I had it. This thing only depends on the quotient, on the image of x in G modulo H, and so that has n things. So here I'm taking the union of n things. But each of this, the cardinality of this is 1/n of the total. So the only way it could be equal to the whole thing is if it was a tessellation, if they were disjoint. But these things are never disjoint because they all contain the identity. So their union by the pigeonhole principle has to omit something. So there's something in the group that you don't get. That is the Frobenius of infinitely many p's. Anyway, forget it. That's a stupid lemma. But the point is I just proved my first claim, which says that there are no algebraic numbers, except irrationals, of course, in A. So that would seem to say that the algebraic closure of Q is itself in A. In other words, Q is an algebraically closed subring of A. Sorry, it's not quite that, but there is no other closure. The algebraic closure within A is just Q. There are no others. But that's not true at all. You see, A contains plenty of algebraic numbers. Let me give you an example. I'm going to find a number y in A as follows. Yp is the smallest solution of x cubed congruent to 5 mod p, if there is one. And otherwise, it's, for instance, 7. And that's certainly a number mod p for every p, right? It's 7 whenever x isn't, that's whenever that thing is no equation. Well, then you'll see this defines a perfectly well-defined thing, and it obviously satisfies this equation. Right? I mean, for every p, either y is 7 or else y cubed is 5. Well, that's certainly a polynomial in z of y. So it is the root of a polynomial, and so it is in the algebraic closure of q bar. The problem is it's not an irreducible polynomial. Over q, when you think of your usual algebraic numbers, they are solutions of an irreducible polynomial, and you can assume that because if you're a solution of any polynomial, you're a solution of one of the factors. But of course, A has lots of zero divisors. For instance, the thing which is 1 at all of these primes and 0 at those, and the thing which is 1 at all of these and 0 at those, the product of those two numbers is 0, but they're each non-zero. They have infinitely many non-zero components. So there are plenty of zero divisors, and therefore the whole notion of algebraic independence. So originally I stated that, since zeta of 3 is known by a priori to be in Q, but it's not known to be transcendental. Everybody conjectures, but we don't know. But I was first claimed that, the Z3, which numerically is also irrational, if some p-adic or finite version of a priori kind of a person could prove that irrationality, they would have proved the transcendence. But in fact, they wouldn't have because of this reason. And in fact, the Z3 can vanish for many p's. I won't go into that, but there are two p's known, I think, where Z3 is 0 mod p. So this Bernoulli number occasionally is 0, and it's just like what I told you about the 2 to the p minus 1. It's conjectured to be true infinitely often. In fact, I think it's even the same piece. Okay, so now let me go on to more interesting theorems. Well, actually, I think I'm going to skip the discussion of the Sun sums, because even if I talk for more than 1 hour, if I don't talk for 2 hours, I won't have time to tell you everything. So the proof of the business with these Sun sums, that so I'll just give you a little table to tell you how it goes, but not give you any proofs, although the proofs are very amusing, and I was planning to give one of them, but as usual, I'm much too slow. So, it's a terrible problem. Okay, so let me try to give you a little table. So this doesn't go up any higher, but this at least goes lower. So remember we had this V of ij. And so let me give you a little table. J is 1, J is 2, 3, 4, 5, 6. Well, I know how this sequence goes on. Okay, so let me give you a little table. So remember, my first examples, I was a positive number. So first I can move up the board. You'll remember, I hope, that J was here 1, 2, 3, 4, 5, and 6.
Wasn't
No, you missed one out.
Yeah, the whole.
If you move down.
If you move it down,
Further
it was moon sheep. Look, H equals 1, 2, and
Ah, I felt that I'd drawn enough things. Thank you. My audience has woken up and is now functioning well. Okay, thank you. Okay, this was correctly numbered as it happened. Okay, so let me now insert this table. I already told you the VI1, I told you the Bernoulli numbers, and I even gave you a little table. So here are the first few, minus 1 over 30, 0, 1 over 42. Okay, then the next column I told you are also rational numbers. They're quite pretty ones. And there's actually a formula for these. In a sense, there's a formula for each of these columns, but they become more and more complicated. And at each stage, you have to do a finite amount of work to work out which coefficients it is. So for each given column, after a finite amount of work, you can give a complete description in closed form. So this is one of the ones I put in my little table at the beginning. Okay? 76 over 2205. So if I go on to 3, well, I told you those are still rational numbers. It starts minus 3, 23 over 18, minus 5 twelfths, 217 over 2250. And so, no, I have plenty more, but that's enough. But then the next time, as I told you, it's already trickier because you get this Z3, which is almost certainly irrational. And it's, sorry, I miswrote. That was the next one. 12 minus Z3 is the second one. The first is minus 24 plus 2 zeta 3. And in fact, the next one is minus 136 27ths plus 1/3 Z3. And the next one is this famous 14 ninths, which is the one that Sun started with, which is from the original table. But again, you get these. So as I already told you, the coefficient of the Z3 here is twice the Bernoulli number. So, I did something slightly terrible. This is no, the numbers are correct except this one. Remember when I copied it, it was off. There's an I equals 0 that I should have included because the theorem is actually for I greater than or equal to 0. These numbers are still rational. The Bernoulli numbers start with 1, not with minus a half. This is minus 2. This is 6 minus 24. So it's an obvious pattern in n factorial. And in fact, it goes on. 120 minus 720. The pattern goes on, but the theorem is no longer true because this is the Z3. And so when I wrote before this, I had actually, I'm sorry, I moved it by 1 in my table. So everything is up by 1, sorry, 14 ninths, and this goes here. Okay, and similarly, well, the next thing, I already put the 120 here, minus 10 Z3. This one is always minus a half of that one. So this is minus 60 plus 5 Z3. And here, I think these numbers, up to a factor of 5, are just these numbers. So it's minus 10, 5, and then minus 29, and so on. And then here you already get a new number, which is in fact, in this case, Z5. So I'll just write one of them. This is minus 720 plus 60, Z3, plus 29, Z5. And then, as I already told you, this column goes down with other rational combinations, but of 1, Z3, and Z5. But now, as I already also mentioned, the I, unlike the J, you're allowed to go backwards. And now is where you get actually the multiple zeta values, because now at 0, now I better put some lines so I don't get completely confused. So at minus 1, you get here 0, here this zeta 3, 0, here 6 zeta 5, or this special zeta 5. Here you get 5 halves z3 squared. And here you get 279 eighths. Something has gone totally wrong with my picture. 0, Z3, 0, 6, Z5. 5 halves. Oh no, it's fine. Just this line is no longer there, right? It got erased. Okay, so my picture is absolutely fine, or maybe it... No. Everything was fine except I copied the wrong number. It's very hard to do this in real time on the board. This is a capital zeta 7. So 92. So you see here you're getting funny zeta numbers. And now if I continue, Z3, 0, 7 halves, Z5, 2/3, Z3 squared, 279 eighths, Z7, and so on. The next one involves Z3, Z5, but then a new generator, which actually occurs somewhere else first, so that's why I didn't call the whole thing that generator, but this combination, etc. And as you continue up, what happens here is that you just get 0, Z3, 0, Z5, 0, Z7, and so on. And similarly, in the next column, you get Z3, 0, Z5, but here you get minus a third, Z3 squared, etc. Now what happens is if you look along a diagonal, then I'm doing this wrong. No, I'm doing it right. If you look along a diagonal, then everything here is Z3, everything here is 0. This is all 0. These are all Z5s. The next diagonal, it's either 0 or it's Z3 squared. The next one will always be Z7. The next will be always a combination of Z3, 5, and Y8, which you actually see in that column for the first time. So what happens now is, actually in the world, it's very easy to see that these V of ij for I negative are in the Z, which is the span of all of my finite multi-zeta values. That's very easy to see. And, sorry?
Is this extra Y8 generator present on all cells of the diagonal?
Well, no, they're only, well, no, that's what I just explained. This is 0. These are both Z3, so it's weight 3. This is weight 2, but there isn't anything. Here it's weight 4, but there isn't anything. Here it's all weight 5, so it happens to be one-dimensional. See, these are all integer rational multiples of Z5. These are all 7, so this Y8 will only come on this diagonal. It only has 6 entries. It only has 6 entries, so it will not come infinitely often, which is what I thought you asked.
No, but I'm asking whether it appears in all of these 6 entries.
Well, that's a question. I mean, it's a random choice of basis. So you're asking whether in the particular basis that I personally chose, each of the 6 finite, I mean, it's only a finite list of vectors, what I'm saying. There are only 6 or 7 vectors in that space. That's what I was, if you, let me finish the sentence I was about to say and then I'll answer the question. What I was saying is these numbers were not homogeneous. For instance, here, I had a combination of 1, 0, 1, zeta 3 and 0, 5. So these are weight 0, 3, and 5. But the full multiple zeta space is, which is the presumed, well, we don't know it's the sum, but presumably the direct sum, I mean, certainly in all the experiments which have been done quite far now, if Zk is the span of, well, I should put an A here. This is ZA. The usual, the script Z is a subset of R. It's the span of all of the multi-zeta values. And now I do the same for these A things. So here I take 8 of K, where the total weight, you know, the sum of the Ki's is K. So these things were not homogeneous. This was mixed, and it weighed 0, 3, and 5. And that's because here my I was positive, which means it's, you know, it was n to the I, h of n to the j. But if you think that h of n involves denominators, 1 over usual multiple zeta values, I should have negative powers. So you should think of this really as negative numbers, and this is positive. And here it's mixed. But these are homogeneous. So all of these are weight 3. And so the conjecture is, here's K, and here's this vector space, ZKA, which is certainly finite dimensional, which is just the span, and there are only finitely many indices. Now they don't have to be admissible because there's no convergence issue, so the Ks are simply positive. The last one is allowed to be 1. But I can tell you the conjectural answer. Well, here it's certainly true. This is 0. This is 0. For 3, it's spanned by, so I'll give a basis. So if I give a base, it's not 0, it's the empty set. For 4, it's 0 dimensional, it's the empty set. For 5, I have Z5. For 6, I have Z3 squared. For 7, I have Z7. And for 8, I have Z3 times Z5. And a new generator, Y8. But as I say, I chose it at random. I mean, if I actually tell you where it comes, it's in weight 8. So if I take the third column, no, even here it'll come. So it's Z0, Z5. The next is minus a third Z3 squared. The one of that is Z7 with a 1. And the one above that I call Y8. So I just took its first occurrence. So it's kind of random. And in fact, I can now answer, well, 1 to the left, it doesn't occur, and all the others, as it happens, it does. But it's a random choice of basis. I could have also chosen that as a basis. There's nothing sacred. But let me just finish a little. So what I'm saying is this space is by definition finite dimensional. But the number of these is 2 to the k minus 1. In the case of real multiple zetas, because of the admissible condition, you have 2 to the k minus 2 tuples of a given weight k. but they span a space which is conjecturally very much smaller dimension. Like for 8, I think it's 5-dimensional. Here it's only 2-dimensional, it's yet smaller. And these numbers, and that you can show easily, that if I is negative, then Vij belongs to the zeta space, and that's very easy to show, homogeneous of weight I plus j, comma a. In other words, these are homogeneous. Here you have only Z3, it's a one-dimensional space, whereas these things are mixed, and that's why it was more complicated. Okay, but what basis I choose? So this you can say if I want a multiplicative set of generators, then since these two were unique up to scalars, I'm forced to choose Z3 times Z5 as part of my basis. But I could choose any vector which is not a multiply, but it's completely meaningless. I just chose that when it was the first one in my table.
So you're saying the first entry is canonical?
No, it just happens here. You have an algebra, you have a vector space, and if you happen to have an element in it which is non-zero, then you could choose that to be part of the basis. But then you have to extend the base. I'm not saying there's anything very special about this. If I go on, there'll be lots of monomials. I'm just saying it's conjecturally at least a free algebra. So free algebra, you can take algebra generators. Then your additive generators are monomials and the algebra generators. So in that sense, if I choose to do that, then having had no choice here and here, I'm forced to include this in my basis, but I can extend anything I want. But of course, I could take any other base. It's just a vector space. You can take any basis you want. And I don't understand the question.
There's a random choice involved how many Z3, Z5 you absorb into the Y8.
It's a random choice. You have a vector space. Look, I mean, I don't know what you're asking. You have a vector space. You pick any vector and any other vector, and that's a basis. If they're not proportional, it's not absorbing a number. They're just any two vectors. Take any two elements of this, and it's a basis. I just chose two at random. But if I want the union of the basis I take here to be the monomials in a set of generators, then this one is fixed in this particular case of 8. But if I go on, it'll be, when I get up to, for instance, 11, then if I've made this particular choice, I'll have to take Z3 squared Z5. Of course, I already have to take Z11, and I have to take Z3, I wanted to Z3 squared Z5, but of course I'll have to take Z3 times Y8, and then I can add some U11. But of course, if I'd taken a different Y8, this wouldn't have been, there's nothing canonical anywhere. I mean, let's not go on to this. It's not an interest. There is nothing canonical as far as I know. These are vector spaces, and I've just chosen a basis.
But you said you want to have Z3, Z5 in it.
I said I didn't want to, but I said one natural thing if you have a free algebra is to take algebra generators. In that case, since this is unique because it's one-dimensional this, then one of my base elements will be this. But it's still not unique when I go a little further. That's what I just showed in weight 11. Even if I did this Y8 was free. Then if I want algebra generators, I'm forced to take my basis to contain Z3 squared Z5, Z11, Z3 times Y8, and a new one called U11, but this is only canonical after I've chosen that. If I chose a different Y8 prime, this wouldn't be canonical, and nothing is canonical. It happens that this is canonical because it's one-dimensional, but I mean, it's only one-dimensional for two or three values of the weight. I mean, in general, these are just huge dimensional vector spaces. The dimension goes up exponentially. So for instance, the dimension is 10 billion. You have to choose 10 billion elements. It may be that 1 billion of them are already on your list because they're products. So if I want my list to be closed under products, some base elements are sort of forced by that choice, but even they aren't God-given. They're only chosen in terms of the previous choices. So I mean, it really has no meaning. Only the Z's have a meaning because Z is really Z.
I'm sorry,
Yep.
I have a typos question. It's on the VIG in Z on the left of the board, just above the Z above, like either like at the really top of the gap here, and this something written over the Z, and he says Z is generated by the zeta.
See, it's the same statement. I just wrote it twice. Here I wrote if I is negative, then I said it's very easy to see that if I is negative, Vij is a combination of multiple zetas. And here I was a little more precise. I said not only it's in there, but its weight is I plus j. So for instance, it's on this antidiagonal. If absolute value of I is 4 and j is 3, then it'll be weight 7. Or, I mean, it's just the sum.
But I didn't get how the Z n are part of the finite multiple zeta value set.
Z and which?
So the big ZA, above its equal to the things generated by the finite multiple zeta value.
This is by definition. This is the definition. So that this is in there is by definition. ZA, I defined it here, is the span of all of these things.
Yeah, but the Z3, for example, the Z3.
No, Z3 is not zeta 3, as I explained in great detail. Zeta 3 is 0. However, Z3 is, oh, you're asking about the Z, not the V, sorry. There were too many identical sounding letters. You're asking why is Z3, which I carefully explained is not Zeta 3, which in fact happens to be 0, why is it in Z3 at all? And that's an utterly 100% legitimate question. The answer is it's ZA of 1, 2, or 2, 1. Actually, it's both, and 1 is plus or minus, and 1 is minus or plus. I'd have to look. So it is in that algebra, but it's not the same as zeta 3. That's right. I didn't catch what you were asking. Thank you. I of course meant to say that. So these z's, now it's not obvious why the base elements I'm writing are even in the space. Because Z3 I defined in a way that was different from zeta 3. That's also a one-line check. I mean, that's really easy. In fact, another very easy thing, which I proved, and then Kanek told me it was in, there are at least 2 papers in the literature where it's written as a theorem. To me, it was just one of various identities. So it's quite easy to prove, but very amusing. I'll also skip the proof because time is short. That's for the double. So there are a lot of specific identities, but I was going to say a little about them, but I think I'm going to skip it. So there are many identities. And I have a list of special ones. That's like the lecture I gave here 2.5 weeks ago on special identities for multizetas, but it's much more interesting to talk about the structure. So I'll just give 1 or 2 very simple examples. So one that, as I said, we have, and it's very easy, but in fact it's in the literature twice. Hoffman wrote about these things, I think even several years ago, but I only found that out a few days ago, and I still haven't actually got a copy of the paper. It's now in my Dropbox because Kaneko will have sent it, but I haven't yet looked at it. And I simply didn't know, and also more recently Zhao, and now there are new reprints by other people. They didn't talk about the ring A, they just looked at each value modulo P separately, but proved the same kind of theorems. Hoffman gave the dimensions, so in particular if I take the dimension, I'll give you a formula in a second, a table of the dimensions up to 15, rather than only up to 8. He gave a table up to 9, but it was that was several years ago, but it was hard to make the right conjecture from his table because there were 2 mistakes in it, as he told me a few days ago. I had never seen it, so I didn't know that. 2 of his numbers he miscalculated, and then a preprint which just appeared in the archive very recently, he told me about, those 2 numbers were correct, and they made a conjecture which is the same as the one I'd made. I did this about 3 years ago, and I'd calculated up to weight 12, and Kaneko has calculated up to 15, but he said he can easily go further, and will in the next few days. So one can calculate these dimensions, of course numerically, for quite a long time. But let me give an example. So this is the one that's in both Hoffman's paper and one of the papers by Zhao, the exact references, and it says that the double zetas always reduce to the single zetas, of course not zeta A of k, which as I explained to you already is 0 for all k. So the multizetas when you specialize to single are uninteresting, but if you take the other definition with the capital zeta, or z, then you just take z of that weight. So that's not only true for 2, 1, but it's true in general. So any double zeta is a multiple of this zk. So the double zetas of any weight span a one-dimensional space, if the weight is odd. Otherwise, it's 0, because that number is equal to 0 if a plus b is even. As we already saw, that zk is then 0. But the theorem is true in all cases with a uniform proof. And it's also, not quite trivial, but it's a 3-line proof. It's very, very easy to do that case. I mean, obviously, if anyone wants to see any of these proofs, just ask. So let me now remind you a little the usual conjecture. There's the standard conjecture. So we have, remember, this z, which is the sum, and conjecturally the direct sum, of these zk's. In R, this was the span of the usual z of k's, where here, since it's a real number, k is admissible, and of weight, a given number. And so the conjecture is, there was a conjecture I made many years ago, that the dimension of the zk, so the greater dimension of the pieces, is dk, and it's known by Terrasoma and Gonchadov and Talinia, and now there's actually many, many other proofs that it's bounded above by that. Nobody can prove any independence, so it's only known that it's, well, the trivial result is greater than or equal to 1. Nobody can prove anything of independence. And dk is defined by the generating series 1 over 1 minus x squared minus x cubed. So in other words, you have k and dk. Before I erase the table, let me also put the conjectural dimension for dka. And so the conjectural dimensions here I'll fill it in a second, but I first want to copy from here. So here we saw that there was well, here I don't know what to put. Probably it's again 1, I guess. Here it's 1, 0, 1. I'm just counting. The dimension seems to be 1, 0, 1, 1. For 7, there's only 1. For 8, there are 2. And now I can continue. So here, this just means, of course, that dk is equal to dk minus 2 plus dk minus 3. And therefore, it's very easy to compute these things inductively. So each one, this 9, the 5 is 2 plus 3. This is 3 plus 4. This is 4 plus 5. This is 5 plus 7. And here, the conjecture, so this is the old conjecture, and the new conjecture, which is probably can also be proved in one direction, but it hasn't yet been done, is the dimension of zka is equal, so this is conjectural, with dka, where the sum dka, x to the k, is the same thing that multiplied by 1 minus x squared, which means it satisfies exactly the same recursion except for the beginning. So after you've done the beginning, you just do the same recursion. So 1 is 1 plus 0, this is 1, this is 2, this is 2, this is 3, this is 4. And in fact, you can see easily that there's a simpler formula for this.
dka equals
So-
dk minus
Yeah, and that's trivial, of course, but this is the way to look at it, I assure you, not what... so, of course, from this, we immediately see that dka is dk minus 2, and now by the recursion, that's the same as dk minus 3, if k is at least 3, as indeed you see here. So, but that's actually not the way to look at it. This is the correct way to look at it. It's not shifted by 3 in some weird way. It's multiplied by 1 minus x squared. And so that means that dka, or dka, is conjecturally equal, if I combine the two conjectures, to the dimension of zk, well, z star, modulo pi squared times z star. This is a ring and it contains z of 2 and hence pi squared. And then if you quotient out by the ideal generated by pi squared in weight k, then of course the dimension of that is dk minus 2, and that's the correct way to look at it. So the idea is that there are exactly as many of these as there are ordinary multiple zetas if you simply set pi squared equals 0. Remember when we try to define zeta of 2, then traditionally, this one is pi squared up to rational numbers. This is something new, 1.202, you can't express it. This is pi to the 4th, so it's expressed in terms, so this is the new number. Here, when we took simply zeta a of k, then it was completely boring, we got 0, 0, 0, 0. But even when we corrected to z of k, we got these new numbers, capital zeta, z, z3 and z5, we still couldn't do anything for 0. No, it's as if pi squared has become 0. And that remains true experimentally. So I've done this up to weight 12. Kaneko has now gone up to 15, but will very soon have gone further. Should I say a word about how you compute these things? It's not obvious. So for instance, when I find on the computer that, let me take one of the examples from the table. I've erased the table, so I'll copy one entry. So a typical entry, for instance, was that v of 4, 6 is minus 29 30ths z5 plus 142 over 225 times z3 minus 1,530,311 over 253,125. So that's all very well if I just write this on the board, but how do you find that? I mean, how do you find these numbers? So what you do, for real numbers, it's well known. If these were all real numbers, 1, zeta, 5, zeta, 7, zeta 3, excuse me, and this number, then you use what's called the LLL algorithm, Lenstra-Lovász, and it's programmed on many software systems, and you just apply it, and it will find a linear dependence over Q among real numbers if you have the real numbers to sufficiently high real precision, and if the coefficients aren't too big. Otherwise, of course, you can find an approximate equality for everything. So now what do we do? Well, when you think what that means, so now you've given me, let's say, 4 numbers in A, and when I say you've given, that means that for all primes except some small ones, you've given me an actual number modulo p. So let's say, and here I have that because I can compute everything here mod p. That's also not obvious because if I take zeta of k, p, then a priori there were p to the r, well, over r factorial terms because it was r tuples of numbers. So if p is, for instance, 500, which is typically how far I go, and r is, for instance, 12, then this is way too big for any computer. But actually, there's a very, very trivial algorithm, and the actual algorithm is not p to the power r, it's p times r. Okay, so if the prime is 500 and r is 12, you have length 12, it's O of 6,000, which in Paris means a fraction of a second. So these numbers become extremely easy to compute, mod p. So now when I say that I have these, it means that I know AP, etc., BP, CP, and DP for, let's say, since I want to avoid some small primes, although it doesn't matter, because if there's a small prime, you just multiply the whole thing by an integer and you'll kill that small prime. But let's say, well, 500 isn't a prime, so I should just say, let's say for all primes between 30 and 500. So I take, for instance, all primes between 30 and 500, and I compute these four numbers exactly. That's exact arithmetic. It's an integer mod p. And now I want to know, question, conjecture, did there exist A, B, C, and D in Z, not too big, otherwise it's of course trivially true, such that AA plus BB plus CC plus DD is 0 in A. So I'm looking for linear dependencies, like this one. Well, if you think about it, of course, that's the same as saying that if I put P everywhere, then this is congruent to 0 mod P for all P. Well, I mean, I've chosen to do the primes between 30 and 500. So now what I do is I take these numbers A, I lift A, B, C, and D. Since I know the modulo P for all of these primes, I can think of them as integers, modulo capital P, where P is the product of all of these primes. So this is some gigantic number with, 300 digits, but Paris happily calculates modulo large integer. That's very, very easy, because you never need more digits than the size of P. And now our question is, we want AA plus BB plus CC plus DD to be 0 mod P. But to be 0 mod P simply means that it's a multiple of P, and if you think about it, A, B, C, and D, I can choose between 0 and P. So each of these, since little a, B, C, and D are small integers, not too big, therefore this is something not too big times P. So when I divide, this E is just P. So when this multiple, E is also not too big. So if I have such a relationship, then I'll have a 5-tuple with A, B, C, D, E, where they're all not too big. And now I can simply divide this, well, here I can just put P. So I'll now divide by P. Is 0. And now I simply change these rational numbers, which is a huge numerator over this huge common denominator. I just changed it into a real number, which I now have to 200 decimals. And so now I have exactly the situation that I already know how to solve. I have 5 real numbers, and I'm looking to very high accuracy to 200 decimal digits, but real numbers. And now I look for a relation among Q using the classical LLL, but in one dimension higher. So that's the trick, and it's 2 lines to program and works fine, and you can easily calculate to any kind of precision. So of course, when I say that conjecturally, if I say that D8A is equal conjecturally to whatever it is in this table, which I stupidly just erased, but 0, 1, 2, 3, 4, 5, 6, 7, 8, 2, what I mean is that I find 2 numbers, which were the Z3 times Z5 and the Y8 that Oliver and I were squabbling about. What I've proved is only that it's either greater than 2, equal to 2, or smaller. I've proved nothing at all. Because I don't know that those 2 numbers are independent. I only know that if there's a dependence between them, it has hundreds of digits of coefficients. So I think they're independent. So I think the dimension is at least 2. And all I know the other way is that all of my numbers up to P is 500 were linear combinations. So modulo this 300-digit integer P, this is true that all of the others were small combinations of these, but of course I don't know what will happen for the next prime. So the dimension could be 1, it could be 6. I haven't proved anything, but it seems to be 2, but to extremely high precision. You have the same caveat for the real numbers. When you say that experimentally D12 is 12, you only mean that to very high precision, there are 12 that seem independent. If they're dependent, it's a very complicated dependency, and they seem to suffice for all the rest. If they don't, then you have something very funny happening in the numerics. So now I want to come to the really most interesting part, which happened here in the Newton Institute when Matsunobu was here for a couple of days before the activity on multiple zeta values. And we talked. So following well, first I'll just say what you do. I'm going to define new numbers. He calls them S, but I'm going to call them F for finite. So I won't say where the ki's are for the moment. These are going to be real numbers. And so these are F for finite, but these are finite real multiple zeta values because they lie in Z. And I'm going to define them as the following sum. Let me do it, I'll put the sign when I need it. So I take the first I of them, where I goes from 0 to R. So if I is 0, by definition, zeta of the empty set is always 1. That's the only consistent definition. And then I take the other ones, the remaining ones, but first I change the sign by the sum of all of the weights that occur. And then I reverse the order. So this is clearly something in ZK, in R, in the usual zeta algebra, where K is the sum of all of the weights. But it's a linear combination of these things. Now, I didn't yet tell you where the KIs are. For the moment, I need that all KIs are at least 2. Before, I only needed the KRs at least 2. But now every KI will eventually be the last number. And so the way I have to find it, this is only a sum of products of real numbers if every K is at least 2. But in fact, using the shuffle product, which is sometimes, I sometimes use shuffle and star. Maybe I will do shuffle and star, you can also say shuffle and stuffle. It turns out that you can make generalized. This was certainly something Ekal had done many years ago, and I'd done many years ago, both unpublished, and I eventually published my version in the joint paper with Ihara and Kaneko. You can make renormalized values where K is now simply an end of the R. Remember that Z of K as a real number only existed if KR is at least 2 for convergence. But you can generalize in 2 different ways. There's a shuffle generalization and a shuffle generalization. But the difference is that these are both polynomials. They're no longer real numbers. They're polynomials in a variable t. And the degree, well, if my K is K1 up to some KR, and then which is at least 2, and then I have a certain number of, let's say, S. So if KR is the last one that's bigger than 1, sorry, it's the last one that's bigger than 1, and then I have S1s, then both zeta shuffle and zeta, the other one, will be actually Z of this K1 up to KR part over R factorial T to the R plus O of T to the R minus 1. So the leading term is as it was before, with the same, they both have the same leading term, but the rest is different. And now this thing is set up, so in particular if S is 0, so if it was convergent, then of course it just stops. It's a constant polynomial, then it's the old value. So these are the renormalizations, and the point is that it's very well known that when you multiply zeta values, K1 times K2, that you can do it in 2 ways, the Stuffle sum or harmonic product and the shuffle product. So you have 2 operations on multituples. This is not a single multituple, but a finite linear combination, so it's a finite combination. But this you do with the star, and you have a similar one where you do the shuffle. So for ordinary finite zetas, there are 2 ways to combine the indices, both of which represent the product. And therefore you get the famous double shuffle relations that since the 2 products are the same, these things are the same, that gives you a relation among not products but linear combinations of zetas. But when you do the regularized thing, then this is true for both the shuffle version and the stuffle, but you need different regularizations, one to make one product rule hold and one to make the other product rule. And they're completely determined by this product, plus what I already told you that they all agree K and the usual K if K is admissible, in other words, if the last entry is at least 2, and they both have the product with either, I'll just put a dot, meaning either one. If you just take the original one, it's the polynomial t, just to normalize it. So zeta of 1, which is infinite, is t. So t represents this infinite quantity, but then everything else is a polynomial. And actually, these turn out to be polynomials whose coefficients are, by induction, previous rational zetas. So that's just to remind you. And so now, because I had this problem, when I do this, I could put, let's say, A here, and here B, where each of A and B is either shuffle or stuffle. Okay, so there are 4 possible ways to make this dimension. And now I could let the KIs be greater than or equal to 1, but this is a priori in R of t. And so there's a proposition that all 4 of these are in R. In other words, each of these are polynomials in T. And they're different polynomials, whether you take A to be shuffle or stuff, and those are different polynomials. But if you always take A on the left, the first one always to be, let's say, shuffle, and the one on the right always to be stuffle. So there are 4 combinations. Each of those polynomials of T you get is constant. And so these are actually, that's why I use F for finite. These are really finite in the sense that even as T goes to infinity, they don't depend on T. But the 4 of them are different, but experimentally, the one we're actually using is the stuffle for everything I'm going to say. But I asked Masanobu last night, and he said that up to weight 10, he'd already checked, and he'll check now up to weight 15 or 20. If you take shuffle or stuffle, you seem to always get the same one. So, each of these is a real number, not a polynomial. So I'm getting 4 real numbers. Each is in the usual zeta algebra. And 2 of them seem to always be the same. The other 2 are neither the same as each other nor the same as this, but the differences are very small. So typically in some natural Z bases, these have extremely complicated coefficients, and the 2 other ones, most of the coefficients are the same, and the others differ by small integers or something. So it's nearly independent of the normalization in small weights, but that's all a little mysterious. So as I say, I'll just fix it. So to have a well-defined definition, so this is a definition. Since I have to make a definition, the one he actually used is the harmonic product or the stuffle product, so I'll use that. So this is the definition, and as I said, the way I defined it, this is a polynomial in T, and that the things on the right are polynomials in T, but the proposition, these are polynomials in T, but this is a polynomial independent of T. So it's in R, and actually it's in Z. So these are finite ones. So now comes the really amazing thing. We sort of thought, there seemed to be absolutely no reason. We thought we would try it out on the computer, and now it's worked for the first many thousands of examples. So conjecture. If I take these finite k, now remember k is simply in n to the whatever it is. So it's an R tuple. There's no admissible condition anymore because, as I just told you, to make sense of this, you don't just need that kr is at least 2, you need that they're all at least 2. If you don't have that, you need these polynomials, but then the polynomials always turn out to be a constant polynomial. And so in fact here, k1 up to kr are arbitrary positive integers. So now I can look at this in z star modulo pi squared. Remember my conjecture for the dimension based on, I'd done it up to weight 12, now up to higher weight, was that the dimension of the space of these finite multiple zeta values in the sense of being in the poor man's ideals in A was the same as this ring, the original multiple zeta ring modulo pi squared. So here I have a collection, and here I have my zeta A of k in this poor man's ideal ring satisfy the same relations over Q. And they form a ring that you can show for the zeta A of k, and that is, you can actually show it's the same stuffle product, so that in other words, we actually have a map. If I send Z A to Z star modulo pi squared Z star, so i.e., if that's true, then you would have the fact that there's, if I simply map zeta A of k to the usual zeta of k, this finite value, but modulo pi squared, so I set pi squared equal to 0, then this is well defined. And that's the hardest part, that it's well defined at all. I mean, it looks fine because I've told you where everything goes, but of course these things have a huge number of relations. And then if a relation here, which is 0, were to go to something not 0, it wouldn't be well defined. So the claim is any relation here maps to relation, so it's well defined, and it's also injective and it's also surjective. So it's an isomorphism of rings. So that's the final statement that maybe since I've gone well over, let me just look at and there were many other individual identities and a few other general statements. I'll just mention some of the things. In the usual zetas, there's a sum formula. Kaneko had discovered one here that has now been proved. Another identity in the usual case was a conjecture I'd made many years ago that Brodpers proved zeta of 1313, and the usual was pi to the something over pi to the 2 times something over something, so that should be 0, and that has also been proved. That was conjectured, no, it was proved. I have all the names. And there's a duality that Hoffman proved, and there's a parity result. That's the one last thing that I should say. So that is a theorem that we had conjectured then proved. Theorem, the depth of zeta f of k1 up to kr. So the depth of a multiple zeta value is not just r, because that's not well defined. You have lots and lots of relations. The depth is the best depth you can achieve. If you have any combination of multiple zeta values, you can write it in many other ways as a combination of multiple zeta values. You try to make them as short as possible. And the best depth you can achieve is called the depth. So the depth is, by definition, is at most r, because I've already written it. But it always goes down. So this is depth dropping. And in fact, it goes down by 2 if k, which is the sum of the ki's, is congruent to r mod 2. So I remind you of this is the parity result, but it's the parity result for the a's. The second is parity. So this is depth dropping, depth reduction, and the second is parity. So I remind you of the previous parity statement, which was proved in a paper by Ihara Kaneko and myself, and probably by other people. Certainly Egal knew it, and undoubtedly other people in the field, I have no idea who knew what when, but anyway, it's a theorem that the usual zeta case has depth, well, of course, it's always less than or equal to r, so I won't say the non-trivial case, if the weight is not equal to the depth modulo 2. So, for instance, that was a result of Euler. When r is 2, this would say that if the weight is odd, which is therefore not 2 mod 2, then any odd double zeta, so zeta of a comma b, where a and b have opposite parity, such a thing always reduces to a product pi squared, well, some even zeta times some odd zeta. So the more general parity result is that it always drops, where you have to have a little caveat. If r is 1, then this would say that every single zeta doesn't exist if k is even, but Euler tells you it does exist, it's pi to the 2n, and so the right interpretation is here also you should think of this as modulo pi squared in some sense, but it doesn't affect any of the other values. So this is the usual statement that the depth is usually r of this thing, but can be r minus 1 half the time. But here it's never r, it always drops. So we saw the first example that zeta a of k was always 0. That says it drops, and since it was already 1. And we saw the next one, I gave you the result, that zeta AB was always equal to a multiple of this zk, which means when I do it for zeta f, then this one does become zeta of k. So the depth is times some rational numbers, some binomial coefficients. So in the world of these finite things, all double zetas, I don't know why I capitalized it, all double zetas drop to a single zeta. And then on top of it, if k is even as well, then it drops to nothing at all because it's pi squared. So the second part is a trivial consequence of the first part and the old parity result. Because once you're down here, if the parity is wrong, you can drop one more. But the point is it always goes down. It's a very easy proof. I was going to prove it, it's 3 minutes, and then I would have proved something, but I'll admit it because I've talked for an hour and a half. So I'll stop, and you can ask questions, for instance, what that proof would have been, or something like that.
Thanks very much. Any
And
questions?
thank you, Masanobu, if you're there. Yeah.
Maybe he has questions as well.
Right. I don't think there's any way to communicate
Yeah,
that.
but maybe
One way.
questions from the audience.
Could we maybe just look at the weight 8 example of the zeta finite? What could you say about a sensible Q basis of weight 8?
Well, I gave it to you, and we talked about it, you and I, for several minutes. I'm such a generous guy. I'll answer not only that question, but the same question as far as I have it listed here, which is up to 15. Takes no time at all. So here are algebra generators up to weight 15. Okay? So I'll do them. So we first start with zeta of a n. So this is double, depth 2. But as I told you, this is the zeta a. And so when you go to the zeta f, you take the same thing defined as I just did, although it looks like it's double. I mean, it is double as it stands. But remember, this would be zeta of 1n finite, would be zeta of 1 renormalized times zeta of n, zeta of 1 comma n, plus or minus zeta of 1 times zeta of n, plus or minus zeta of n comma 1, and then the claim is the depth is actually 1. So although I wrote depth 2, I won't even write it. These are really depth 1 in some sense. So up to weight 10, this is weight n plus 1, and you already saw that these were the zk's. I mean, it's very easy to see that zk is the same as z1k minus 1, maybe up to multiple k. I forget, but they're proportional. So these are the numbers that are previously called z3, z5. So 6, 8, 10, 12, and 14. Then we have 1, 1, n. And now n is again even, but the first one, which is not already in what I had, so presumably this goes on, but up to weight, presumably you can, I mean, of course the numbers exist, and they're presumably part of the basis of generators. So the next set is 1, 1, 1, n, and here the first one that we didn't already have is for n, and 12 is the last one where the weight is at most 15. Then I can take 1, 1, 1, 1, n, and here n is 8 or 10, and I can take 1, 1, 1, 1, 1, and n, and the weight is 10 because this is 5, so that's the only one on that list. But in each case, you could put an arbitrary even number, and then the next case is 1, 2, n, and here the first one that we didn't have is 9, and it has to be odd by the parity result, otherwise it would drop. And similarly here, if it's 1 and 3, then this number has to be even, and the only one is 10, and that's the complete list. So here, that I meant to say anyway, this is the complete list experimentally, but I remember that in weight 15, there are already 2 to the 15 minus 1 multiple zetas at that weight. So altogether, when I add it all up, there are 2 to the 15s, that's 30,000. So for the first 30,000 multiple zetas, they are all linear combinations and homogeneous of products of these things. So in particular, in weight 8, this one, remember, Z3, this is Z5, this is Z7. So in weight 7, you have Z3 times Z5. These I could call Y7, excuse me, Y8. The weight is 2 more. This is Y10, Y12, Y14. And these have some new name like X11. So in weight 8, it's these two, if I chose that basis. So that's the basis in weight 8. But here's the complete multiplicative set. So in weight 15, the dimensions, I think, 12, or whatever it is, I have it written down, and you just work out from the formula that we had, and then it's just all products of these things that have total weight 15. So up to 15, we have this, and we have no particular conjecture yet, although we're close. Well, we're seeing more and more structure. It's changing almost daily. So I think these have a lot of structure. I mean, the selling point of these is it's much easier to calculate the way I showed you, mod this large integer p, than with real numbers. Well, not just that. That's not easier because you use the same LLL, but it's much easier to compute. To get this to 200 digits, it's a real number. I need that capital P to have 200 decimal digits. That means I take 80 P's or something. That's just nothing at all. I mean, the first 80 P's is the P's up to 500 or something. I can easily take the first 2,000 P's, and then I have a number of 800 digits. So where it's very slow, I mean, Broadhurst can do it. He can compute to 20,000 digits. But even for him, that takes a long time. And so if you want to do very high precision, the usual multiple zetas, it's a lot of work. And so people store their results in a data mine, but this you can practically recompute each time. And the individual computations are very, very fast. So these are, and therefore it should be much easier to do numerical computation. Also the theory looks better. And now these new zeta f's that are defined here, and this theorem that this is actually a finite thing is very beautiful. There's no reason for that. I mean, it's not a very difficult proof, but it's a very beautiful fact. I had a really, really pretty idea, which unfortunately is wrong, that would have given a natural reason to write this thing down, but unfortunately came out exactly the other. See, there is a natural way to make it finite, which is just say, how about if I make a modified, I'll call this f prime, some other. I take the usual definition. But these are no longer positive integers, they're simply integers. I put a prime to say that I emit 0. So that's a very natural definition. Just sum over all integers, positive or negative. Well then, assuming that all the k's are at least 2, so I don't have convergence problems, and then you can try to do the renormalization, you can see if the first I of them are negative, then this will be the sum. It will be exactly the same story as above, but in the opposite order. I mean, if everything is at least 2. Except that this time, you take the first ones and reverse it, and the others you leave in their given order. Here we took the first I and kept the order, and we reversed the last R minus I. So it's exactly the same thing with the other way. And this would be really natural. And again, I have 4 versions. I can put A or B, shuffle, 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 shuffle. Unfortunately, none of them are finite now. So it didn't work. This other way of doing it It's very similar. Had it worked, I could have just taken the Cauchy principal value, leaving the limit between minus m and m as m goes to infinity. That would have been a beautiful definition in one line, not this artificial definition with the sum of products. But unfortunately, this thing, which has the sum of products, is exactly equally complicated, it's slightly different. This one doesn't work. This is not finite. So you have to do this. And it's motivated, as I said, by a remark of Kontsevich. I mean, maybe I should say that. He does the same thing mod p. He says, you know, when you have your thing mod p, p is very large. So you can think of these as some number which is much bigger than n, but much smaller than p. That's part of your sum. So the zeta finite thing at p. You have the thing where all of the arbs are small, but another possibility is that they're all very big. Or you can also have some of them, you know, the first ones can be small and the others can be big. And then the limit of that is exactly, this becomes that real number, this becomes that real number. And so he said, in some sense, the natural real analog would be this one. And then what he hadn't checked, but we did, is that this is only the natural analog that has that wonderful property that it's finite as a polynomial in T. It's the constant polynomial. So you get a natural embedding into the real numbers, and then the real beauty, which nobody expected, is that it worked now with the double shuffle. So I hope this will actually be proved in a reasonable amount of time. It shouldn't be unprovable.
I have some question. What the list on your list? It is shown that these are non-zero.
That which?
Yeah, zeta.
Nothing is shown. No, nothing is shown. Sorry, which one?
So all the list here, zeta 111n, 111n.
No, of course, nothing is shown.
Not shown. Even to show non-zero is not so.
It's certainly not so. So I've said, for instance, that for Z3, well, non-zero is just the question that this dimension is not zero, but it's equally interesting to note that dimension is not 1 instead of 2. In other words, the real question to be is to prove that Z3 is irrational. So nobody knows that. But in fact, we don't even know that Z3 is... No, that I think you could prove. So if Z3 were 0, that would say that P divides BP minus 3 for all P bigger than some P0. That I think you can prove is impossible. I think, but I'm not sure. But we definitely cannot prove that there are, you know, that it's not always just some fixed rational number. It's the same kind of thing. We cannot prove anything. So, and in fact, there are two values of P which are known where BP minus 3 is 0 mod P, but they're very big again. So this is sometimes 0 mod P. In other words, Z3 is surely not 0, but it's definitely not. Well, no, it's almost certainly not a unit in A. Because we expect that the number of primes where P divides BP minus 3 is infinite. So in that case, this thing is infinite many zero components. So if it were only finitely many, then in A0 it would be a unit. But in A it would be a unit. But we believe that for sure that they're infinitely many. And so this is not even an invertible number. And maybe it's even 0. We can't prove anything about. That's like asking, can I prove that zeta 5 is irrational? You know, that's independence results. Nobody can prove, even for the real numbers. So you can't expect that. We can only prove identities, but not non-existence of identities.
So I'm curious whether. So I was thinking about Z1.
Z1?
Well, which obviously, I presume from what you've told us, this doesn't make sense. BP.
Well, no, it's infinite, yeah, just as it should be. Zeta of 1 is infinite. Z1 unnormalized doesn't make sense because BP minus 1 is, of course, has a P in the denominator.
Yeah.
So no, there is no Z1.
And
it starts with Z3.
logarithmically divergent? That was my first question.
I don't
know. There's no further P's in the denominator.
Oh, sorry. Well, we were talking about mod P. I mean, if you're, I don't know quite what you're asking. If you're asking about the feeling, we can talk about feelings all day. Z1 does not exist. It cannot be defined directly. That's the first thing. And the second is that numerically up to weight 15 with these generators, and the first generator occurs in weight 3. There is no generator, neither Z1 nor anything else.
Yeah.
Now, if you ask about multiple higher powers, that's a whole other question. Very natural. Can you lift this to P squared? And the answer is yes. Somebody that I met, a German, whose name I blog on, that I met in Utrecht, had heard me once give a preliminary talk on this, and he went away and played multiple higher powers of P already with the sun sums, and he found similar things but with more terms. So if you work multiple P squared, then were I a two-dimensional space, his was 5-dimensional, but it's still finite-dimensional, multiple P squared. And those coefficients he couldn't identify, but I could. They were the same as in my table, just in a different position. So there is a story you can go mod P squared, and presumably mod P-adic, it's for somebody else to play with. I haven't thought about it, so I don't
in fact,
want to...
my question was going to be more like, is there an analog of L of 1?
There's no L here, so I don't know.
There's no way you can...
I don't know what you mean by L of 1.
Well, so
There's no L.
incorporate some sort of Dedekind.
But you can't do that even for real zeta values in any reasonable way,
I see.
despite talks that we heard. There's no analog of multiple zeta values with Dedekind zeta values. I mean, you can define something, but they have no shuffle relation. None of this story applies. But anyway, I really don't want to talk philosophy. Is there a question? I mean, it's philosophical questions. Can one, there's no. Of course, anything is possible. That somebody will find a generalization, but then that's just speculation. It's not a well-defined thing. Is there a generalization to something? But so far as I know, already over
Well, the
there's
answer is
no
no.
reasonable.
I mean, I was asking a question to which I didn't know the answer, and your answer was no. That's fine.
Well, if you were asking whether I know of one, that's a
Okay,
question
that may
about
be
my
one.
knowledge. But I
Okay, so
didn't hear a
just phrase my
mathematical
question.
question.
Okay.
I didn't hear a mathematical question, like is something true or false. You said, can one invent some generalization of something? Well, maybe one can. I mean, I haven't, and I'm not, and I don't believe it's in the real case you can't. There's no multiple Dedekind zeta function in any reason. I mean, of course, you can define something with some inequalities, but there's no double shuffle, so there are no relations. The interest, to me, in multiple zeta values is a fascinating algebra where you have a huge number of relations that you don't expect. If you define multiple zeta values, then all the values are linearly independent. There's one shuffle, but that you can do for anything. It doesn't have to be zeta, and there's no second shuffle. There's not, to me, any convincing definition yet. And there are several candidates, but none of them have any of this algebraic structure. So the beauty here is that this thing, not only is a similar structure, but it seems to be the same structure. Not just the right number of relations, but the same relations. So somehow this is a finite model, the usual one, but much easier to compute it. And then what you asked about z of 1, you said something about p squared, and there I said there is a stored multiple p squared in higher powers, but I haven't followed it. I've looked a little at what this person did, and there's no reason in the proofs that you can't go one step further or two steps, but it becomes more and more intricate, and we haven't tried. So that will be for other people. Yeah?
Can we count double shuffle relations for these finite multi-zetas?
I think the answer to that should be by next Monday. So one shuffle relation is easy, and the second one, Masanobu said he didn't, but I mean, we've just been working, all of this is the last week or so, and I was traveling, and he was being the dean, so we haven't had too much time. He had a proof that this thing was finite using the algebra, so code products and so on. From that he couldn't see much. I had a proof, an analytic proof, I'm using this as real numbers, and from that I get an integral representation, but I haven't yet written it down. So I can probably do it by tomorrow. Once you have the integral representation, then you can multiply it for the, not for the A ones, for the F ones, for these real finite zetas. So the question first is, do they satisfy a double shuffle? So one shuffle is easy. These shuffle with respect to the shuffle product all by themselves. But the other one should come if you have an integral representation, you should get a different one. And now we have an integral representation, but I haven't yet written down to see what it gives. And so there should be two shuffle relations, and then that will at least tell us what the relations are among these finite ones. But since experimentally we have the same relations for the A ones, then we'll at least know what the shuffle relations are. It's also possible that the answer maybe it will not be known by next Tuesday, but it was already known a couple of years ago, because it may be in Hoffman's paper. I haven't read it. I only heard about it a few days ago, and I don't even have a copy yet. Masanobu has read, and I asked him on the phone, because Hoffman proved one thing, this parity result. I should have said that. He proved this parity result already for the zeta A's. I proved it for the zeta F's. But my proof, even the old proof that we gave for the usual ones, used the double shuffle, not just the single. So I think Hoffman, if he proved it, must have a double shuffle, but I haven't seen his paper. So maybe the answer is it's already known, but not to me. And if it's not known yet, it will be by Monday. I'm sure there is, because you can't get all of these relations if there's not two shuffle relations. One shuffle relation is useless. You can take anything and make one shuffle relation. Just take any sum over integer sequences. So I'm sure the answer is yes, but I can't yet write it down because I haven't done it yet.
This parity result, is it really different, or is that just a misprint? So it should be k not congruent to 1?
No, k congruent. It's the opposite, of course, because it's shifted by 1. It's 1 less. It's already r minus 1. I mean, this is a trivial consequence of that, as I said, because it's already gone from r to r minus 1. But if k is r mod 2, then r minus 1 isn't k mod 2. It's the opposite. And therefore, by a previous result, that one falls by 1 more. That's a trivial consequence. Once it's fallen once, it falls twice half the time, because there simply aren't any zetas in that parity and weight at all. I mean, they all fall, right? And therefore, this is... So the second is sort of just in parentheses. It's a comment. But the main point is this, that it always falls by 1. And therefore, indeed, it's the other way around. As indeed you saw, that zeta of k was always 0, even k was even rolled. I mean, it's really 1 less. Everything, it really is, honestly. So, for instance, zeta of AB was a multiple. of zeta of a plus b. Remember, some binomial coefficient times zeta of a plus b, and so it is 0 if a plus b is even. Whereas in Euler's thing, it was if a plus b is odd. It's really the other way around, because there's a shift of the weight by 1. And as I should have mentioned, there's a sum theorem, but there's also a duality theorem, and the duality also you shift by 1 everything. So there's and we know why now, finally, as of yesterday. So it's all a bit in flux.
Okay. Thank you, speaker again.
So I propose that we have a 30 minutes break.